Right, let's go through this exercise then. The first question was, where should the base of the smoke layer be allowed to descend to? Well, the base of the smoke layer should be at least 0.5 metres above any opening that needs protecting. And in this case, it seems reasonable to protect the first floor opening against fire on the ground floor. So we shall adopt a height of 9 metres plus 0.5 metres, which gives you 9.5 metres from the equilibrium height at the base of the smoke layer. Therefore, the smoke layer will be 32 minus 9.5, 22.5 metres. That's the depth of the smoke. Now let's look at the second part, which is basically use the 11-step guide to determine the requirements of the atrium. Let's look at step 1, the design objectives. Well, these are specified as life safety. In other words, to maintain the clear layer height 0.5 metres above the highest opening. And this is for life safety. And also, it will have an impact on property protection. You've also got to ensure that the smoke temperature is not excessively high as to break the glass. So they're the design objectives. Let's look at step 2. We need to determine the design fire size now that's going to be adopted in the scheme. Now we have to establish a design fire size. Now we've done this from table 3.3 in BR368. You can see that a fire in a sprinklered office may grow to cover 16 square metres, with a perimeter of 14 metres and a convective heat output of 2,700 kilowatts. So that's from table 3.3 in BR368. That's where we got this data from. Now we're going to use the higher figure of 2,700 kilowatts as we don't actually know where the fire may be in the room. And if it's near the opening, then we can expect the spill plume to carry the greatest heat flux. Now, it's not possible directly to reconcile the area of 16 square metres with a perimeter of 14 metres, but we can take it to be this because the fire is going to be approximately 3.5 to 4 metres square. So that's where we got that from. That is our design fire size. Now, let's work out the mass flow rate of smoke. Step 3, the mass flow rate of smoke. Now, we firstly need to establish, remember, whether it's a simple plume or a complex plume. Well, in this case, it's classified as a complex plume because the atrium itself is free of fire loading. The plume will therefore have to enter atrium from an adjoining space, so it's a complex plume. Now, in this case, we've got to identify which spill model we're going to apply from the complex plume. And this is because with 2 of the models available, you have to determine the mass flow rate of smoke out of the opening and along the balcony, and then this is used as an input in the model for the spill plume. However, with the other 2 models, you don't. Yet the spill plume, you can work it out without knowing the mass flow rate out of the opening. The mass flow rate of smoke is more dependent on the opening sizes and the fire size. So as you can appreciate, if you're determining the mass flow rate of smoke in the atrium only, you look at the spill plume models first. Whereas if you're carrying out slot extraction or under balcony extraction, you must determine the mass flow rate of smoke out of the room of origin and under the balcony. Do you understand? So, also 2 of the spill models require this information as inputs, and so you do have to determine it. The height of rise is the distance from the lowest spill edge to the base of the smoke layer. That is from 3 metres above ground to 9.5 metres above ground. In this case, it's 6.5 metres. So that's the height of the rise of the smoke from the spill edge. Therefore, in this case, the most appropriate model to use is the guidance in PD 7974 Part 2 to calculate the mass flow rate. So that's the one model we're going to use with this spill rise. This is the model here. M smoke equals 0.36 times QP to the third times L to the 2/3 multiplied by brackets HR plus 0.25 times HS times 50%. Now, if we put in our data into that formula, as you can see here, you put all your data in, you should have got a mass flow rate of smoke of 41.6 kilograms a second coming on. That's the spill plume, is 41.6 kilograms per second. Now we know the mass flow rate of smoke. Now we need to work out the temperature of the smoke. Now there's 2 temperatures of concern with us. First of all, you've got to check it's at least 20 degrees Kelvin above ambient, especially for natural, because if not, it won't actually reach the vents to get out. So you've got to have at least 20 degrees Kelvin above ambient. And also, in this case, the smoke temperature cannot be too high, because if it is, it may shatter the glass. If it's excessive, the glass may need to be fire resistant or at least heat resistant. Let's determine the temperature of the smoke then. Well, the formula to determine the temperature of the smoke is as follows. Theta equals QP divided by MC, where theta is the temperature rise, QP is the convective heat output in kilowatts, and M is the mass flow rate of smoke in kilograms a second, and C is the specific heat capacity of air. You put them in here, you've got theta equals 2,700 divided by 41.6 times 1.01. You should have got a theta value of 64 degrees Kelvin. So that's the temperature increase of the smoke. Now, we're happy with the smoke now. I've got enough buoyancy. It's over 20 degrees, so it's not going to pose a problem for reaching the vents. However, it's also not too excessive so that we need fire-resistant glass, because the glass will never get hot enough. It's only 64 degrees Kelvin rise. So now we know that answer. We need to work out the actual average temperature of the smoke. For these, we'll need this for inputs later on. So how hot is the smoke? And to work out the temperature of the smoke, you use this. TL equals TO plus theta, where TL is the absolute average temperature of the smoke, TO is the ambient temperature of smoke, and theta is your temperature increase. If you'd have put them in, you'd have got the temperature of the smoke to be 352 degrees Kelvin. So that's the temperature of the actual smoke itself, 352 degrees Kelvin. Now, we know how much smoke we've got and we know how hot it is. Now we need to start determining how we're going to extract this smoke. Now, before determining this, you have to consider stratification. And this is covered in step 5, the stratification check. Now, stratification in this atrium is very unlikely. However, for completeness, we will carry it out using this formula. Let's work out the Z max. This is the formula here. Z max equals 5.54 times QP to the quarter times delta T delta Z to the power of minus 3 over 8. So let's look at the variables. This is where Z max is the maximum height the smoke will rise. QP is the convective heat release rate. Delta T is the temperature difference between the top and the bottom of the atrium. And delta Z is the height of the atrium. Now in this case, delta T we've said is 0.3 kilowatts per metre. You multiply that by the height, you get 0.3 times 32. You should have got 9.6 as a delta T. And your delta Z, you know, is 32 metres. Now, putting in these variables, you should have got a Z max of 62.72 metres. So that is the Z max. That's the maximum height that the smoke can reach. Well, clearly in this case, it can rise to a height of 62.72. The atrium height is 32 metres. So in this case, we know it is not going to stratify. So that check's done. We can move on to step 6 now. Now, step 6 is determining the ventilation requirements. Now, it's been established that we're adopting mechanical ventilation, so let's progress with this in mind. We're going from mechanical ventilation. Now, the first thing to determine is the number of reservoirs that you're going to have in your building. Now, the largest size of a reservoir in a mechanical system is 2,600 square metres. However, this can be increased to 3,000 for property protection only. Now, in this case, it's immaterial anyway because there's only one reservoir and it's got a size of 1,450 square metres. Next, because we're looking at mechanical ventilation, we don't need to determine the aerodynamic free area, but we need to work out the volumetric rate, and this is based on our design fire size. Now, to determine the volumetric flow rate, you use this formula here. V equals M divided by rho 0 times TL times TO, where V is your volumetric flow rate in metres cubed a second. Your M is your mass flow rate in kilograms a second. Your density is in kilograms per metre cubed. The absolute temperature of the smoke is in TL. And TO is your ambient air temperature. If you'd have put those in, you'd have worked out your volumetric flow rate is 42.37 metres cubed a second. So you need to extract a total of 42.37 metres cubed a second. That's what we need to do. So that covers step 6. Now we're going to look at step 7, which is determine the number of ventilators in the reservoir. Now we know that the proposed fans, as we said, have a capacity of 11 metres cubed a second. And in this situation, you do not have to assume a fan was lost. Sometimes you have to take out a fan if there's a reason to believe a fan could be taken out. In other words, if the stores are right next to the fan, it could take it out in a fire. Well, in this case, the atrium's sterile, so it's very unlikely a fan will be taken out. So you can progress on the assumption that no fans are taken out. Now we know the volumetric flow rate is 11 metres cubed a second. If you divide it out, you've got 42.37 divided by 11. Therefore, you need 3.85, or you need 4 fans. So we need 4 fans in that reservoir with an output of 11 metres cubed a second. That covers step 7. Let's move on to step 8, which is the stagnation check. Now remember, with mechanical ventilation, there is no requirement for stagnation checks. You don't have to do it with mechanical. So again, we can go straight on to step 9. Now step 9 is the plug holing check. Now this applies to both natural and mechanical ventilation. Now don't forget, there's 2 models to determine if plug holing will occur, and this depends on where the ventilator is located. Now the model to use when the ventilator is more than 2 metres from the edge is shown as follows. This is the model here. Now in this case, the smoke layer depth is 22.5 metres, which is way higher than is likely to plug hole. Don't forget, a general guide is, if it's less than 1 metre, the smoke layer depth is very likely to plug hole. And if it's over 5 metres, it's unlikely. In this case, it's 22.5 metres. However, let's check it. It's unlikely, but let's check it. Let's work out what the MCRIT is. You put all your known variables in the MCRIT. You should have got an MCRIT of 1,427 kilograms a second. That's how much smoke has got to leave each ventilator with that layer smoke out before it's going to plug hole. Clearly, this amount of smoke will never be leaving each ventilator, but how much smoke is likely to leach each ventilator? Well, this is the formula to apply. You've got to convert it from a volumetric flow rate into a mass flow rate to compare it with your MCRIT. This is your formula here. MCRIT equals V fan times your ambient temperature times your ambient density divided by the temperature of the gas layer. If you'd have put those in, this formula here, you'd have got an M fan of 10.8 kilograms a second. So that's how much smoke is leaving each fan, 10.8 kilograms a second. Well, this is clearly less than the requirement for a plug holing. So what you're going to say is plug holing is not likely to occur. Let's move on to step 10 now, which is to check the air inlet velocity if necessary. Now, this is a mechanical system, so you do have to check that the air velocity is not going to exceed a certain amount. So don't forget, this has to be done is to ensure that the replacement air coming in through the exit doors and any automatic opening events is not as high as to impede escape from the building. So as it's coming in, people trying to escape. And in this case, it's an office environment with an inlet area of only 8.2 square metres. So they've already said there's 8.2 square metres of openings allowing air in. Now, the maximum velocity that is allowable for the incoming replacement air is 7 metres a second for an office building. Don't forget, if it's the general public coming in, you've got to reduce it down to 5 metres a second. Now, we need to check the air inlet velocity using this formula here. AI must be greater than or equal to your Vmax divided by your UV, your velocity, times your C, your coefficient of your inlet. Now, if all the fans are using, there's 4 fans extracting, you've got to assume all 4 kick in. So you've got 11 metres cubed a second from each. It gives us a total extraction rate, which is your Vmax, of 44 metres a second. Now, you put those in, your aerodynamic free area is AI. You basically must be greater or equal to, you've got 44 divided by your 7, which is your 7 metres a second. Your coefficient of your inlet is 0.6. It gives you an area of 10.48 square metres. This tells you that if you have less than 10.48 square metres of inlet air to replace the smoke that's been extracted, then the velocity of the air will exceed your acceptable velocity of 7 metres a second. Therefore, you now have to increase the air inlet to 10.48 square metres. Now, this can be done by installing more automatic opening events. However, they must be installed lower than the smoke layer depth. So whatever air inlets are coming in, you've got to make sure they're all below the smoke layer. Now, that completes step 10. We now move on to step 11, which is your post-design considerations. You've got to consider weather conditions, whether tall buildings are going to impact on your ventilation requirements. Generally, for mechanical, it doesn't matter. It's mainly for natural ventilation systems. Also, there are no smoke curtains, so you don't have to carry out deflection checks. You just got to make sure your maintenance now and your testing, all your other requirements are satisfactory. And that completes this exercise.